Hey, welcome back. In my last video, we discovered the derivative, a way to find slope at a single point, also called the slope of the tangent line or the instantaneous rate of change. The way to find derivative is by using the limit definition, the limit as h goes to 0 of f of x plus h minus f of x over h. But as you worked more and more of these problems, as you practiced this skill, you probably started to notice a little bit of a pattern. And that's what we're going to address today, the shortcut to taking derivatives, the power rule. Let's start off with a simple idea. A constant function, like y equals 4, a straight horizontal line, has a slope of 0 everywhere. Every point on that line has a slope of 0, therefore the derivative of a constant is 0. And I want to point out, this ddx right here, for now that means take the derivative of. So when you see ddx, take the derivative of whatever comes next, or differentiate whatever comes next. So the derivative of a constant is 0, makes sense. The next part, the power rule, is really what's important here. The derivative of x to the nth power is n times x to the n minus 1 power. So for example, if you have x to the third power, the 3 comes in front. I have 3x to the second power. The exponent goes down by 1. And using the power rule, we can differentiate basic polynomials much faster and easier than we could with the limit definition of derivative. Okay, let me show you. In example 1, we're asked to find the derivative of 3x minus 4. Okay, now I want to state the obvious for a second. This 3x is actually 3x to the first power. So when I take the derivative of 3x to the first power using the power rule, the 1 comes in front. 1 times 3 is 3. X to the 0 power, because the exponent goes down by 1. So I've got 3x to the 0 power minus the derivative of 4, that's a constant, which is 0. X to the 0 power, of course, is 1, so 3 times 1 minus 0 is 3. And again, think about what we're talking about. 3x minus 4 is a linear function. Its slope is 3. At every point on that function, the slope is 3, so the derivative is a constant value. In example 2, ddt, hey wait, there's a t here, not an x. That's okay. It just means take the derivative with respect to t because what comes next is an expression involving t's instead of x's. Don't sweat it. Take the derivative of 4t squared minus 4t plus 8. Okay. Well, using the power rule, the derivative of 4t squared, the 2 comes in front. 2 times 4 is 8. T to the first power minus the derivative of 4t, just like the 3x up above, the derivative of 4t is 4, plus the derivative of 8 is a constant, so it's 0. So my derivative is 8t minus 4. And example 3, find the derivative of 3x to the fourth minus x cubed plus 3 halves x squared plus 4x minus 10. Okay, as long as it's something times x to a number power, we can use the power rule. So even though there's a lot of pieces, each one independently is pretty easy. My derivative is going to be, using the power rule, 4 times 3 is 12, x to the third power minus 3, x to the second power, plus 2 times 3 halves is 3, x to the first power, plus the derivative of 4x is 4, minus 0. There's my derivative. So to find the derivatives of polynomials using the power rule and the constant rule together, what was an arduous process has become fairly quick. Now, the next most important thing to learn is how do I take a problem that looks difficult and rewrite it in a way that allows me to use the power rule. I want to take functions and rewrite them so that it's a number times x to a power whenever possible, because that allows me to use the power rule, and the power rule is easy. So look at example 4 with me. Take the derivative of 1 over x cubed. 1 over x cubed is not a number times x to a power, but I can rewrite it. I can rewrite 1 over x cubed as x to the negative 3. And see, when it's written like this, now you can use the power rule. The derivative is going to be negative 3 times x to the, be careful, lots of people make mistakes here, negative 3 minus 1 is negative 4. So the derivative of x to the negative 3 is negative 3x to the negative 4. Now, you can leave your answer like this, or if you want to write it in the style that the question was originally written in, it would be negative 3 over x to the fourth. Both are correct. Example 5, same issue. Find the derivative of the square root of x. Okay, I want to see this written using exponents. So I'm going to rewrite this problem as take the derivative of x to the 1/2 power. Remember, fractional exponents, the number on top is the power you're raising to, the number on bottom is the root that you're taking. So the 1/2 power is the same thing as the square root, and when it's written this way, I can use the power rule. The derivative is going to be 1/2 x to the negative 1/2. And again, just like that is fine, but if you want to write it in a clean way, it's going to be 1/2 x to the 1/2, 1/2 square roots of x. And finally, example 6, we've got 4 over the cube root of x squared. Again, how can I rewrite this so I can use the power rule? I'm going to rewrite this as the derivative of 4x to the negative 2/3. Negative because it's in the denominator, 2/3 because it's the cube root and it's being squared. Now that it's written like this, I can use the power rule, the derivative of 4x to the negative 2/3. Negative 2/3 times 4 is negative 8/3. X to the negative 2/3 minus 1 is negative 5/3. Okay. And that answer is fine like that, but make sure you know how to simplify it. I can also write this as negative 8 over 3 cube roots of x to the 5th. Both are good. Next up, example 7. Write the equation of the tangent line and stop right there. Before you read anything else, as soon as you see equation of the tangent line, did you think point and slope? Because you should. That's immediately what you're going to think anytime you see the words tangent line. Find the equation of the tangent line to f of x equals x cubed plus 3x at the point where x is negative 1. So my point is going to be negative 1 comma something. How do I find the y coordinate? Take negative 1 and plug it in. Negative 1 cubed is negative 1, minus 3 is negative 4. How do I find the slope? Well, I want the slope at that point. So I need to plug negative 1 into the derivative. F prime of x, this is now much easier than it was in our last day of notes. Using the power rule, my derivative is 3x squared plus 3. So f prime of negative 1 is going to be 3 plus 3 is 6. So the slope at this point is 6. Got my point, got my slope, point-slope form. Y minus y1 equals slope x minus x1. It's that easy, as long as you remember point and slope. Example 8, write the equation of the tangent line of g of x equals 2x cubed plus 4 over x squared at the point where x equals 2. So I do see equation of the tangent line, so I know I need to find point and slope. So to find my point, I'm going to take the x value that was given to me, 2, and plug it in. So I'm going to have 2 comma 2 times 8 is 16 plus 4 is 20 divided by 4 is 5. So my point is 2 comma 5. But to find my slope, I need the derivative, and this does not look like something I can use the power rule on at first glance. However, because the denominator has a single term, I can split this into multiple fractions. So I'm going to rewrite g of x as 2x cubed over x squared plus 4 over x squared. And notice, I could recombine these. They have a common denominator. This is the same as the way the problem was originally written, but now I can simplify. I can reduce each fraction on its own. G of x equals 2x plus 4x to the negative 2. And suddenly this function looks like something that I can differentiate using the power rule. So g prime of x is going to be 2 minus 8x to the negative 3. Okay? Or 2 minus 8 over x cubed. Now we're going to plug in 2. 2 minus 8 over 8, 2 minus 1 is 1. So my slope is 1. Got my point, got my slope, point-slope form. Y minus 5 equals 1 times x minus 2. And it might seem silly to leave it that way, but hey, I'm done. If you want to add 5 to the other side, be my guest. Example 9, determine the intervals where the following function is differentiable. Okay, let's take a step back and remember, what has to be true to be differentiable? A function needs to be continuous with no sharp turns and no vertical tangents. So when I look at my piecewise function here, the square root of x is differentiable everywhere in its domain, so for every x value from 0 and up, and x minus 2, a linear function, is differentiable everywhere from negative infinity to infinity. So I'm interested in what's happening at 4. In order for this piecewise function to be differentiable, first of all, it has to be continuous. So let's check and see. Is it continuous? When I plug in 4, I'm going to have an open circle at 4 comma square root of 4, so 2. And when I plug in 4 here, I'm going to have a closed circle at 4 comma 4 minus 2, 2. So this is a continuous function. These two pieces come together at 4 comma 2. All that's left now is to determine, do they come together such that the curve is smooth, or do they come together so that there's a kink or sharp turn in the graph? So to determine that, we're going to take the derivative of the pieces of this piecewise function. So f prime of x, well, we have to think of this in nice terms. The square root of x is x to the 1/2 power, so its derivative would be 1/2 x to the negative 1/2. And the derivative of x minus 2 is 1. So now the question is, at 4, do these derivatives line up? Meaning, do these two curves come together in a smooth transition, or is there a sharp turn in the graph? If I plug 4 into the top function, 1 over 2 square roots of 4 is 1/4. If I plug 4 into the bottom function, well, there's nowhere to plug in. The slope is 1. So what I see is, even though this is a continuous function, the slope coming in is 1/4, and then the slope leaving is 1. There's a sharp turn in the graph, so this function is not differentiable at 4. And last one for today, same as up above, determine the intervals where the following function is differentiable. I noticed right away that x cubed and 12x minus 16 are both differentiable everywhere, so I want to know what happens at that breaking point. What's happening at 2? First of all, is this function continuous? When I plug in 2, I get the point 2 comma 8. And when I plug 2 in on the bottom equation, I get the point 2 comma 8. So it's continuous. These two pieces come together at the point 2 comma 8, but do they come together in a smooth way or with a sharp turn? And so I need the derivative. H prime of x is going to be 3x squared for x values less than 2, and 12 for x values greater than 2. And now I want to know what is happening at 2. When I plug 2 into the top equation, 3 times 4 is 12. When I plug 2 into the bottom equation, nowhere to plug in, so I get 12. So not only is this graph continuous, but the slopes are matching up at the point where it comes together. Both are 12. So this function h of x is differentiable everywhere. So to wrap up, today we took our idea of derivative and simplified it with the power rule and the constant rule. The derivative of a constant is 0, and the derivative of x to the nth power is n times x to the n minus 1 power. And we practiced maybe the most underrated skill of calculus, which is taking a problem that looks hard and rewriting it in a way that looks easy, using negative exponents and fractional exponents. Using that, we can find equations of tangent lines much faster than we could before. Hope that helps. Thanks for watching.